Okay, welcome to lesson 5 of module 5. We're going to be talking about graphs of functions and equations. So we're going to be continuing on this theme of functions, and I'm going to be doing an abbreviated version of this lesson so you can follow along in your classwork, but it might look a little different. You're welcome to do the complete version of the classwork by consulting the teacher's notes. Okay, so this first example, which is labeled exercise 1, is just another distance time function like we've been talking about. So the distance that Giselle runs is a function of the time that she spends running. Okay, so the input then would be the time she spends running, and the function is going to tell us how far she goes. So the information we're given is that Giselle runs at a constant rate and that she can run 3 miles in 21 minutes. So we know a little bit, we can figure out what her rate is. So if you haven't done so yet, you can figure out that rate right now, and you could even write the relationship, the mathematical rule that would define this function. So that would be an equation in 2 variables that would give us the distance that she runs as a function of her time. Okay, so since Janelle can run, let me get my color here. Since she can run 3 miles in 21 minutes, we can write her rate like this. We can say 3 miles in 21 minutes. We can simplify that rate to 1 mile in 7 minutes. And then I'd like to write that even more abbreviated, 1/7 of a mile per minute. Okay, she can go 1/7 of a mile every minute. So we could recognize this as a proportional relationship, and we can write the rule as that her distance is equal to her rate, which is 1/7 of a mile per minute, times the number of minutes that she runs. So we're going to have, we're going to do a graph now, and it's going to have her time in minutes on the x-axis or the horizontal axis. Remember, this is our input, and then the output is going to be the distance that she runs. So we can put any number in here for time, and it will give us distance. So the graph of a function is just a collection of points that are input-output pairs. So we can choose some time. So if x is 14, that means she's been running for 14 minutes, then the output would be 1/7 of 14, or 2 miles. Okay, and so here are some of the other inputs. So here's 14 minutes and 2 miles. And then over here, 28 minutes, 1/7 of 28 is 4. So that means she goes 4 miles in 28 minutes. Down here, in 7 minutes, she can go 1 mile. And up here we have one more, 42 minutes and 6 miles. So these are just some input-output pairs that are solutions to this function that work for this function. We're beginning to build the graph of this function. So hopefully you can notice that this is just the linear equation that we've written here. So all the input-output pairs for this function are the same as the graph of the linear equation that defines this function. So I can see that these points are forming a line, and I know that my inputs for this function are all the rational numbers along the x-axis. So I don't have to use whole numbers for x. So this is not a discrete function. It's more continuous. So I can go ahead and draw a line, and that line, that graph of that linear equation, is going to define all of the input-output pairs that works for this function. So that's kind of one of the big ideas of this lesson, is just that if there is a mathematical rule for a function, like there is in this case, y is equal to 1/7 x, then the graph of this equation includes all the input-outputs for the function. Okay, I know there's a lot of vocabulary there, and it's a fairly simple idea, but it's an important one. Okay, for this next exercise, you're given the equation y is equal to x squared and asked to fill out an input-output table, or a XY table, and then also plot the points. So if you haven't done so yet, you could do that on your own, and then come back and we'll discuss this, this equation. Okay, so I'm going to quickly fill out this input-output table. 0 squared is 0, 1 squared is 1, 2 squared is 4, and then I have 9, 16, 25, and 36. And when I go to plot those, I'm going to plot them on this grid here. And so I've got 1, 2, 4, 3, 9, okay, so there's some of those points. There's one more, 36 right here. Okay, so one of the questions you're asked with this is this a linear function? And maybe you can see that this is not linear. These points are actually curving up. This graph is getting steeper and steeper. One way I can see that is by looking at the input-output table, and I can see that even though my x values are all increasing by 1, the change in x for each of these is just 1. It's going up 1, 2, 3, 4, 5, 6. But my change here is 1. But in the next input-output pair from 1 to 4 is 3. From 4 to 9 is 5, and so on. So the slope is increasing, and we can see that on the graph. We can see that the rate of change between these 2 points is much greater than the rate of change between, for instance, these 2 points. This is a steeper slope, and it happens gradually. It happens as a curve. You'll get a lot more into, I'm just going to try to draw a smooth curve there, curves like this as you move on in algebra. So this is a nonlinear function. We know that because of the exponent on the x. We learned that linear expressions only have a power of 1, right, on the variable. So, or 0, 1 or 0. So an x squared term is what's making this be a curve. So, okay, so we can graph or an equation that's nonlinear just by making a table and plotting the points. And so usually need to do more points for a curve than what you did for a line. so that you can see where it's going. And this isn't the smoothest that it could be drawn, but it's pretty close. Okay, let's look at an example related to this now. Okay, so now consider this function. It's right here. The area of a square is a function of the side length of a square. So if I have a square, it has a side length, all the sides are the same length, and I can find the area of that square given the side length. Okay, so the input to this function is s, the side length. And so I can use any positive number would give me, I could use as the side length of a square. It's got to be positive. So those inputs have to be positive. The output is going to be, we'll call it A, the area of the square. Okay, so there's a mathematical rule that describes this function. And you know it. It's that area is equal to s times s, or s squared. Length times width. So area is s squared. So if I were to think about what would the graph of this function look like, it would look just like the graph we just did of y is equal to x squared for all positive x's. So the idea here is that the graph of a function, such as this one, side length of a square and area of a square, is going to be identical to the graph of the mathematical rule or the equation that describes the function. So a equals s squared is going to look identical to y equals x squared. Okay, now we're going to look at some graphs that are just really some sets of input-output points. So I'm going to do just a quick reminder about what a function is. So a function is a pairing, sometimes it's a rule, that assigns to each input exactly one output. Remember, we want to be able to predict outputs from inputs, and so we can't have two different outputs for the same input. So each input has exactly one output or a unique output. The inputs of a function can be discrete or continuous, and we've been calling that not discrete. It's not technically continuous, but the last function that we saw for side length, where the input was side length of a square, that was not discrete, because I could use any rational number, or really any real number on the x-axis could be the side length of a square. There weren't just certain numbers that would work for that. So discrete functions, remember, are individual inputs. And we often want to define what are valid inputs for a function. For instance, the side length of a square can't be negative. So we can define what the functions are. Also this, some functions have mathematical rules that describe them and others do not. And these ones we're going to look at here in a minute don't. Okay, so there's three graphs, graph 1, 2, and 3. Which, if any, could represent the graph of a function? Explain why or why not for each graph. Okay, so if you haven't already, you might want to pause and decide if you think graph 1, 2, and 3 could be functions or not. Okay, so as we look at graph 1, I'm going to take each point and see that this input of -2 has only one output. The input of 0 has one. It looks like each of these input values has a unique output. So graph 1 would be a function. So we can look at the next one. So as we begin to look at this one, an input of 0 has an output of 0, an input of 2 has an output of 3, 4 has an output of 5, but then when I get to 6 here, notice it has an output of both 4 and 6. So what that's doing is it's saying for an input of 6, I can't really predict what the output's going to be. My function machine is going to be playing tricks on me, putting two different things in. So even though all the rest of these have an output for an input, this part right here is what's going to keep this one from being a function. So graph 2 is not a function. And let's look at graph 3. So graph 3 looks nonlinear. It's kind of curving down and around like that. But each input, an input of 0 is 0, an input of 1 has an output of 1, an input of 2 has an output of, or that's -1, has an output of -4. So each of these inputs has only one output. So this would be a function. Now notice there's -2 has an output of -4, and +2 has an output of -4. That's okay. This is still a function. We can repeat outputs. We just can't have two outputs for the same input and still be a function. Okay, in the same way that we just looked at graphs of ordered pairs and determined if they could be functions, we can do the same thing with a set of ordered pairs just written out. So I want to know, could the following set of input-output pairs be considered a function? So what I'm looking for is to make sure that there's a unique output for each input. So I have an input of 3 and an output of 5. And then I can see an input of 4, and then I notice an input of 3 again. So with an input of 3, with a different output this time, here's 5 and 9. So this would not be a function. This one here is not a function because it doesn't have a unique output for each input. So this right here disqualifies it from being a function. Whereas the one below, this set of pairs, I've got, if I check the inputs, -1, -3, 5, and 7, all the inputs are different, so these will have to be unique outputs. So this one is a function because of that. Well, it is a function. Now, this might be nagging at you that there's a 6 here and a 6 here. But remember, because the inputs are different, I can have repeated outputs and still be a function. I just can't have two inputs with different outputs. So, and again, that's because I want this to be a predictor for me. And if I can't be certain of getting the same output every time I use a particular input value, it's not a function that's going to work for me that way. So I can tell from a graph, I can tell from a set of ordered pairs whether it's going to be a function or not. Okay, so let's try it. Just have a couple other examples. So this is graph 1, 2, 3, and 4. Go ahead and pause the video and think about whether any or all of those graphs could be functions. Okay, so let's look at them then. So let's look at graph 1 and see if okay, so graph 1 is a function because there's a unique output for every input. Graph 2 fails in right over here. Pen is not working. Right there, because that input of 1 has 2 different outputs. It has an output of 0 and an output of 2. So graph 2 is not a function. We'll just put not. Graph 3 is also not a function because you can see every input down right here, every input has, well, almost except for this one, has 2 outputs, okay? So this is a graph of a circle, obviously. So this is not a function, even though it obviously has a mathematical rule that's defining it. It does not fit the definition of a function. So this circle here is not a function. Whereas these inputs down here would be. This looks like a linear equation. And each input has a unique output. So graphs 1 and 4 are functions, and graphs 2 and 3 are not. Okay, again, so what we've seen in this lesson is that the graph of a function is just a set of all points, x, y, where x is the input and y is the output. And so if I graph all those points, I have the graph of a function. And so what that means is that if a function can be defined by a mathematical rule or by an equation, then the graph of the function, which is all the input-output pairs, is just the graph of the equation. Okay. And then we did some practice with functions and realized that it's not possible for 2 different points in the plot of a graph to have the same x-coordinate. Because if they do, that means that that input value does not have exactly one output. And so it wouldn't fit the definition of a function. Okay, good luck with this lesson set, problem set. It's going to just give you additional practice and hopefully deepen your understanding of functions and writing these equations and making the graphs. So, all right, we'll see you back here for lesson 6.